In the last video, we have seen 5 different properties of Fourier transform: linearity property, time scaling, time shifting, frequency shifting, and duality. Let's move on to the next property, that is time differentiation property. So, time differentiation property, that means if you differentiate the time signal, how will it affect our Fourier transform? F of t is my time signal. F of omega is the corresponding Fourier transform. So if you differentiate your time signal, how will it affect the Fourier domain? That is what we're going to see in this property, right? So let us prove it. Now we'll take the inverse Fourier transform. D inverse Fourier transform we are considering for this proof, right? Now f of t is equal to 1 by 2 pi integral minus infinite to infinite f of omega e power j omega t dt. Now I am differentiating it on both sides. So differentiate this with respect to t, I'll get d by dt of f of t, and on my right hand side 1 by 2 pi. Differentiate with respect to t. Where is t here? Here, right? This is the t term. So I will differentiate this whole thing with d by dt, right? Now let us interchange the differentiation and integration order. It is perfectly normal to interchange integration and differentiation orders. So first I'll take this d by dt inside, right? This is e power j omega t is the only term that is going to be differentiated by t. All other terms are not dependent on t. So if I differentiate this term, what will I get? I'll get, if I differentiate in e power j omega t, e power j omega t into j omega. This is what I will get if I differentiate, right? Now if you look at this term here, I'll just assume it to be my let us say some x, right? Compare these two terms. This is my x, let us say. Are they both of the same form? Yes, they are of the same form. So what can I write? This is nothing but Fourier inverse, right? This is inverse Fourier transform, right? Fourier inverse of whatever is there here in my x place. Fourier inverse of, in place of x I have f of omega. So in place of x here, what I have j omega f of omega, right? I have j omega into f of omega. So that is going to be equal to Fourier inverse of j omega into f of omega, right? So what is this? d by dt of f of t is equal to Fourier inverse of j omega f of omega. If I take this Fourier inverse to the other side, it is nothing but Fourier transform of d by dt of f of t is equals to, on the right hand side I have j omega f of omega. This is what we are writing it in symbolic form. D by dt of f of t has a Fourier transform of j omega f of omega. So if I differentiate my time signal with t, then my Fourier domain is going to be multiplied with j omega, right? It's going to be multiplied with j omega. Then the next one is frequency differentiation. Now we have seen differentiating the signal in time domain. Now we are going to differentiate it in frequency domain and see what will be the effect on time domain signal, right? Now the general expression for Fourier transform is this one, right? The Fourier transform is given by this expression. Now what I will do, I will differentiate my f of omega and this, right? If I differentiate with respect to omega, this is how it will look. So I'll interchange differentiation and integration. I'll interchange them and I will differentiate this signal with respect to omega, right? With respect to omega. So what will be my differentiation with respect to omega here? F of t is a constant with respect to omega. So I can bring it here. I can bring it outside the differentiation. And d by d omega of e power minus j omega t is nothing but e power minus j omega t into minus jt, right? Into minus jt. So this expression here is nothing but integral minus infinite to infinite some function into e power minus j omega t dt. This is nothing but Fourier transform of that function. That is nothing but Fourier transform of minus jt f of t. So Fourier transform of minus jt f of t is nothing but d by d omega of f of omega, right? That is the frequency differentiation property. Frequency differentiation means we are going to differentiate the frequency domain signal and see how the time domain signal changes. Next one is time integration property. Time integration property. Time differentiation, what did we do? We differentiated the time domain signal. So in time integration property, we are going to integrate the time signal from minus infinite till t. T means till the present time. Till the present time, we are going to integrate it and see how my frequency domain signal f of omega changes. Okay. Now, this signal, this time domain signal, how can we write it? That is what we will first look at. My integral minus infinite to t f of tau d tau can be written as multiplication of two signals, right? Integral minus infinite to infinite f of tau into u of t minus tau. Let us see how. U of t minus tau, u of t minus tau. So how is u of t defined originally? U of t, it is equals to 1 for t greater than or equal to 0, 0 for t less than or equal to 0. Okay. Now I will write u of tau. U of tau. How will I write it? It is 1 for tau greater than or equal to 0, 0 for tau less than or equal to 0. Right, this is u of tau. Now I need u of t minus tau. So how will I get u of t minus tau? From the basic operations on signals? In place of tau, I am going to write t minus tau. Right? It is 1 for t minus tau. Sorry, t minus tau greater than or equal to 0. 0 for t minus tau less than or equal to 0. So simplify this. Is nothing but 1 for my variable here is tau. So if I take tau to the other side, tau less than or equal to t, 0, I'll take tau other side. So tau greater than or equal to t. So this is my u of t minus tau, right? U of t minus tau. So if I substitute these values of u of t minus tau, if I substitute these values of u of t minus tau here, what will I get? I'll get u of t minus tau is 1 only in the range of tau less than t. That means from minus infinite to t. So this is 1 only in the range of minus infinite to t, and in all other ranges it's going to be 0. So this integral limits, my lower limit is still minus infinity, my upper limit will change from infinity to t, right? I can write this as minus infinite to t, this whole integral, plus t to infinite, right? In this range, my value of u of t minus tau is 1. So I have f of tau d tau. In this range, value of u of t minus tau is 0, right? So 0. This becomes 0. So this is my original integral I was looking for. Okay. So this can be written as integral minus infinite to t f of tau d tau can be written as integral minus infinite to infinite f of tau u of t minus tau d tau. Okay. Let me erase everything here. So this is my time domain signal. I am just writing it in the form of this. So what I will do now, I will take the Fourier transform on both sides. Fourier transform of this signal is nothing but integral minus infinite to infinite, integral minus infinite to infinite. In place of f of t, I have this whole signal, right? So this one, this is my this is my signal here, e power into e power minus j omega t dt. I'm just substituting this integral in place of f of t. In this integral is nothing but I'm writing it in a different form. So in place of f of t, I'm going to substitute minus infinite to infinite f of tau u of t minus tau d tau. Now there are two integrals. I'll take the tau term outside. So integral minus infinite to infinite f of tau, and in the second integral I have u of t minus tau e power minus j omega t dt and d tau. Now if I look here, this one, this is nothing but Fourier transform of u of t minus tau, right? This integral, it is nothing but Fourier transform of u of t minus tau, right? U of t minus tau. U here is unit step. U here is unit step. We've already seen this, right? Unit step. U is the unit step signal. Now this is the Fourier transform of unit step. We will discuss after the properties, we will discuss the Fourier transform for each and every basic elementary signal. There we will prove this. The Fourier transform of u of t, there we will prove this. For this property, for the sake of this property, just remember the Fourier transform of u of t is 1 by j omega plus pi into delta of omega. The proof of this we will see in the coming slides after the properties. Okay. Till then, please just remember this statement here, the Fourier transform pair. If this is the Fourier transform of u of t, what will be the Fourier transform of u of t minus tau? What am I doing here? It is just the time shifting property, right? By time shifting property, if I shift by tau. So what is my time shifting property? If you remember the third property we have seen, f of t minus b will have the Fourier transform, f of omega into e power minus j omega b, right? Here f of t is u of t. F of t is u of t. f of t is nothing but u of t, and f of omega is equals to 1 by j omega plus pi into delta of pi into delta of omega. This is my f of omega, f of t and f of omega. So if I shift it by tau, in place of b I have tau. So how will my Fourier transform vary? The same thing into e power minus j omega. In place of b I have tau. So e power minus j omega tau. That is the Fourier transform here, right? The same thing, right? So let me just erase this area and we'll look at the rest of the proof. Okay, so for u of t minus tau, the Fourier transform is e power minus j omega tau into 1 by j omega plus del of omega into pi. The same thing we will substitute here in place of f of u of Fourier transform of u of t minus tau. I substituted the entire thing. Now the variable of integration is tau. This entire thing is constant with respect to tau. I can get it outside. And what is left? Integral minus infinite to infinite f of tau e power minus j omega tau d tau. What is this? This is nothing but f of omega, right? F of omega. So I'm multiplying f of omega inside. I'm multiplying f of omega inside, that is 1 by j omega into f of omega plus pi into f of omega into delta of omega. Where does delta of omega exist? Delta of omega exists only at omega equals to 0. So when omega equals to 0, f of omega becomes f of 0 into delta of omega. This is the one of the properties of impulse functions, multiplication by an impulse. If you look at the second property of impulse functions, it is multiplication by an impulse. So from that property we are getting this part, pi into this exists only at omega equals to 0. So in place of omega here for f of omega, I'll substitute f of 0. So this is how we will get the time integration property. Don't worry about this part. This part we will see in the Fourier transform of elementary signals, standard signals. Okay, so that is the end of time integration property. We'll move on to the next property. Next property is convolution in time domain. So I have two Fourier transform pairs here. So if I convolve the two time domain signals, how will my Fourier transform look? That is the essence of convolution in time domain, right? Convolution formula is this. We have already seen this in the first unit. Convolution of two signals is integral minus infinite to infinite. First signal of tau, second signal of t minus tau d tau. That is the convolution integral. We'll just prove the property here. So let us take Fourier transform of the convoluted signal f1 of t convolved with. Remember, this is the to represent the convolution. We write an X mark surrounded by a circle. This is the representation for convolution. I did not find that representation, so I used this asterisk or star mark here. Generally follow this notation: convolution f of t, f1 of t convolved with f2 of t. You can use this notation in general. Okay. Okay. Now we have to find the Fourier transform of the convoluted signal f1 of t convoluted with f2 of t. So this is in my original Fourier transform analysis equation. In place of f of t, I am going to substitute whatever is there here. Whatever is there here. I have f1 of t convoluted with f2 of t. So in place of f1 of t convoluted with f2 of t, I am going to replace my convolution integral. Convolution integral. Right? Now, similarly, similar to last property, we'll just, okay, this is one method of doing it. Multiplying and dividing the right hand side with e power minus j omega tau. I'm multiplying and dividing with e power minus j omega tau. So if I multiply it with e power minus j omega tau and divide it with e power minus j omega tau, that means I can multiply it e power j omega tau. So e power minus j omega tau, I'll leave it aside. These two I will combine. I'll combine these two e terms. What will I get? E power minus j omega t minus tau, right? T minus tau. Now I'll separate the integrals. First integral will consist of one integral symbol f1 of tau e power minus j omega tau and d tau. And my second integral, I'll take it to be integration sign f2 of t minus tau e power minus j omega t minus tau and dt. Okay. And this t minus tau here, I am going to replace it with just a symbol m. Right? It doesn't matter. You can just leave it as t minus tau also. No problem. So this is my f1 of omega and this is going to be my f2 of omega. So it is nothing but multiplication of the two Fourier transforms, right? If you want to find the Fourier transform of the convolution of two signals f1 of t and f2 of t, it is just the multiplication of their individual Fourier transforms. That is the convolution in time domain. If you look at the statement at the top of the page, top of the slide, the Fourier transform of convolution of two signals is given by the product of their individual Fourier transforms. Right? F1 of t and F2 of t have their individual Fourier transforms. The convolution of the Fourier transform of the convolution of F1 of t and F2 of t is nothing but the product of their individual Fourier transforms. That is what we have proved here. Okay, it's very simple. Now we'll move on to the next property, that is convolution in frequency domain. Convolution in frequency domain. So previously we have convoluted the time domain signals. Now we will convolute the frequency domain signal. Right? This is my convolution integral. There we had t and tau, right? T and tau. Here I have omega and lambda. Similar to them, just the change of the variable. Similar to the previous convolution integral, just the change of variable. Okay. Now let me take Fourier inverse of my right hand side. I'll take the Fourier inverse for this one. Inverse Fourier of 1 by 2 pi f1 of omega convolved with f2 of omega. That is nothing but 1 by 2 pi integral of this whole thing, right? Integral of 1 by 2 pi f1 of omega into convoluted with f2 of omega e power j omega t d omega. So in place of f1 of omega convoluted with f2 of omega, I will substitute my convolution integral, right? I have substituted my convolution integral. Then I'll separate this integrals here. 1 by 2 pi integral minus infinite to infinite. I'll get this outside and I'll take this inside, okay? Not to here, this part. F1 of omega, and what am I left with? 1 by 2 pi f2 of omega minus lambda d lambda e power minus j omega t d omega. So here omega minus lambda, omega minus lambda, I am writing it as tau. Okay, omega minus lambda is tau. Now omega is equals to tau plus lambda, right? Omega is equal to tau plus lambda. So d omega is equals to tau is a, okay, d omega is equals to d tau. Okay, where d omega is equal to d tau. So substituting all these things, I have 1, okay, I'll write it here, 1 by 2 pi integral minus infinite to infinite, again 1 by 2 pi here, right, integral minus infinite to infinite f1 of lambda, f1 of lambda, f2 of tau, f2 of tau, and in place d lambda I'll write it as it is, d lambda, and in place of e power j omega t, what can I write? In place of omega I can write tau plus lambda. So multiplied by e power j, in place of omega, tau plus lambda into t, right? And I have d, in place of d omega I have d tau, right? This is my expression. This expression turns out to be same as this expression. Now what can I do? I can separate these. Right? f1 of lambda, d lambda, and from this term I can take e power j lambda t separately, right? So I can write it as 1 by 2 pi integral minus infinite to infinite f1 of lambda, e power j lambda t d lambda. So this is over, f of this thing is over, and I have one more 1 by 2 pi, right? And one more integral from minus infinite to plus infinite, minus infinite to plus infinite. What I have here, f2 of tau, and here I have e power, what is left after taking out e power j lambda t, e power j tau t and d tau. So this first thing is nothing but f1 of t, and the second expression is f2 of t. So multiplication of both of them, right? It is nothing but multiplication of f1 of t and f2 of t. So from convolution, if you convolute in one domain, in the other domain you will multiply. Previously in time domain we convoluted. There the frequency domain is nothing but multiplication of individual Fourier transforms. Here there is multiplication in time domain and the frequency domain is convolution, right? One domain convolution, the other domain is multiplication. So the next property is modulation property. This is very similar to convolution. In place of the second function we have cos and sine, right? Convolution in frequency domain, what did we have? we have f1 of t into f2 of t. Here f2 of t, if you replace with cos and sine, then you will get modulation property. So we'll prove these properties also. F of t into cos omega naught t. What is cos omega naught t? I can write it in the form of e power j theta plus e power minus j theta divided by 2. Here theta is equal to omega naught t, right? So in place of cos omega naught t, I substituted e power j omega naught t plus e power minus j omega naught t by 2. So I will separate the I will split this linearly using linearity property, right? I can write it as f of t into e power j omega naught t by 2 plus f of t into e power minus j omega naught t by 2, and I will split the Fourier transform for both the terms. The first term Fourier transform plus the second term Fourier transform. So how do I find the Fourier transform for this? We know Fourier transform of f of t is f of omega, right? Fourier transform of f of t is f of omega. Now, what do we have here? We have a phase shift. We have a phase shift in time domain signal. This 2 is a constant, right? So I can get it outside. So no problem. Just forget about this 2 for now. We have to find the Fourier transform for f of t into e power j omega naught t. E power j omega naught t into f of t. We need to find the Fourier transform for this. How will we obtain the Fourier transform for this? There is a phase shift in time domain signal. According to frequency shifting property, if there is a phase shift in time domain signal, there will be a shift in the frequency domain signal. Frequency shift by how much? By omega naught. Frequency shift by omega naught. This is nothing but our frequency shifting property. So Fourier transform of f of t into e power j omega naught t is nothing but f of omega minus omega naught. And this 1 by 2 is there here, so I'll get the 1 by 2 outside. So 1 by 2 into f of omega minus omega naught for this. And here we have minus j omega naught t. If I put minus here, this will become plus, right? Very simple. So for this, the second term, the Fourier transform is going to be f of omega plus omega naught. That is the modulation property, the first modulation property. Similarly for sine, in place of sine, I can write, what can I write in place of sine? In place of sine, I can write e power j theta minus e power minus j theta divided by 2j. So I will substitute that. I will separate the terms based on linearity, and I'll get minus 1 by 2j as a constant outside, and for the rest I will find the Fourier transform, which is the same thing, right? 1 by 2j f of omega minus omega naught minus f of omega plus omega naught. This is the modulation property. Next one is conjugation property. So conjugation property, what happens to the Fourier transform if I take the conjugate of the time signal? So let me take Fourier transform of f conjugate of t, right? In place of f of t, I am just substituting f conjugate of t. Now what I will do, I will take the conjugate out here and make it something like this. I will try to make it something like this conjugate here. Okay. So for that, what can I write? I can write it as integral minus infinite to infinite, right? Integral minus infinite to infinite f of t e power j omega t dt whole conjugate. I can write whole conjugate, right? So if I take out the brackets, f of t will be conjugate, and e power j omega t conjugate is nothing but e power minus j omega t, right? So I can write this step. So what is this again? This is in the form of f of omega. What is f of omega? F of omega is equals to integral minus infinite to plus infinite f of t e power minus j omega t dt, right? Here we have e power plus j omega t dt. So what can I write? I can just rearrange this like this, right? I can rearrange this like this. Let me just show you. Here e power j omega t, I will write it as integral minus infinite to infinite f of t e power minus j into minus omega into t dt whole conjugate, right? I can represent that like this, right? So my this signal, what is this signal going to be? It is going to be f of minus omega, right? In place of omega I have minus omega, f of minus omega whole conjugate. That is nothing but f conjugate of minus omega, right? So that is my conjugation property. Conjugation property. Then the final theorem, final property of the Fourier transform is Parseval's theorem. It is also called energy theorem, or it's also called Rayleigh's energy theorem, or there are there's another name, energy spectral density. Parseval's theorem or energy spectral density or Rayleigh's energy theorem, all are the same. So this statement we already seen this about 10 times. F1 of t has Fourier transform f1 of omega, and f2 of t has the Fourier transform f2 of omega. Then what does Parseval relation state? It states that integral minus infinite to infinite f1 of t into f2 star of t, or conjugate. This is nothing but conjugate, okay? f2 conjugate of t dt is equal to 1 by 2 pi minus infinite to infinite f1 of omega f2 conjugate of omega d omega. Now what will happen if f1 and f2 are same? If f1 and f2 is equal to just f, then this will become f of t into f conjugate of t, which is nothing but square of the magnitude, right? F of mod f of t square dt. What is this? This is nothing but energy of f of t, right? What is the formula for energy of f of t? Of any given continuous time signal, what is the formula? Integral minus infinite to infinite mod f of t whole square dt. That is the energy. So the energy is equals to 1 by 2 pi integral minus infinite to infinite mod f of omega whole square d omega. Basically, this statement states that energy or power in the time domain representation of the signal, energy or power in the time domain representation of the signal is equal to energy or power in the frequency domain representation. That is the Parseval's theorem. For Fourier transform, we are only talking about energy. Okay, power we'll see later in the coming units. So energy in time domain representation of the signal is equal to energy in the frequency domain representation, right? So let us prove this thing. We'll take the left hand side, right? We'll take the left hand side. In place of f1 of t, I'm going to substitute the formula for inverse of f1 of t, right? f1 of t is nothing but, what is f1 of t? Or let us say, what is f of t? What is f of t? F of t is equals to 1 by 2 pi integral minus infinite to infinite f of omega e power j omega t d omega, right? F1 of t will be equal to, here in place of f of omega I'll write f1 of omega. So the same thing I'm substituting in place of f1 of t. Then we'll change the order of integration, right? So how? 1 by 2 pi is a constant, I can take it outside, minus infinite to infinite f1 of omega, and then minus infinite to infinite f2 star of omega e power j omega t dt, right? dt, and this d omega I have it separately. Okay, now what is this here? What is this? That is nothing but I can take this conjugate outside here. If I take conjugate outside, my e power j omega t will become e power minus j omega t. So this term here is nothing but f2 of omega, right? That is f2 of omega. So I have f2 conjugate of omega. So that is my first relation, right? Now when f1 and f2 are same, when f1 and f2 is equal to f of t, then f1 of omega is equal to f2 of omega, right? Then I'll get my second statement, right? So energy, the left hand side is energy in the time domain signal, and the right hand side is energy in the frequency domain signal. So both energies are equal. That is what Parseval theorem states, right? And this is the final thing: area under the time domain curve and area under the frequency domain curve or frequency Fourier transform. So how will we prove this? We have to prove this. It states that the area under the time domain curve is equal to the magnitude of the Fourier transform at omega equals to 0, right? So what is the Fourier transform? X of omega is equals to minus infinite to infinite x of t e power minus j omega t dt. Now if I substitute omega equals to 0, what will I get? Capital X of 0, this is capital X of 0, it's equal to minus infinite to infinite x of t e power j 0 t is nothing but 1 into dt. So area, this is nothing but the area under my time domain signal, that is equal to the Fourier transform at omega equals to 0, right? X of 0. Similarly, the area under the Fourier transform curve or the frequency domain curve I can prove, right? Let me take the inverse Fourier transform formula. X of t is equals to 1 by 2 pi minus infinite to plus infinite x of omega e power j omega t d omega. Now if I make t 0, this will become x of 0, right? X of 0, and here this will become 1. So if I get this 2 pi to the other side, it is 2 pi into x of 0, and here I have minus infinite to infinite x of omega d omega, right? The same thing, right? So this is the end of properties of Fourier transforms. In the next video, we will look at the Fourier transforms for standard signals, right?